Okay, picking up where we left off yesterday. We left off with F. Did we eventually get the right answer? Okay. Ethan, have you done the notes yet from yesterday?
I have not, but
okay.
I can see.
You can kind of see. Okay, so this one, the big trick here was, just like we talked about the other day, split this into two pieces, right? And I don't remember what I did and didn't talk about yesterday, but x over square root of x is x to the 1/2, minus 2 over square root of x is 2x to the negative 1/2. Then we are integrating, right? We integrate x to the 1/2, we integrate 2x to the negative 1/2. Those are the rules we already know. Now, remember, when you have numbers, when you have boundaries, we're evaluating from 1 to 4. Plug the upper boundary in first, minus, and then plug the lower boundary in. This is my math to get there. I end up at 2/3. Did we get it? Eventually, we found our mistakes. Okay? This is the basics. Really, this is what I taught yesterday, isn't it? I mean, I think that's the basics of what we spent our time on. So that's what you missed yesterday.
Okay. So, like, with that answer, is that like the area under the curve at that within that interval?
From 1 to 4, yes. Okay. Yeah, that is. Because it is an integral, that does qualify as the area under the curve from 1 to 4 of whatever that function looks like, which, no idea what that looks like, but yep. Okay. Moving on and looking at the next page. Okay. We did this back with derivatives. And now we're going to look at it a little bit with integrals, antiderivatives, where we talk a little bit more about meaning. Now, when we talk about derivatives, it was more rate of change. When we talk about integrals, we're talking more total change. Okay, so what kind of explanation do we have here when we talk about our real world terms? So, as we look at example A, if f of t represents the rate at which your 401k changes in value over the month of January, units of f of t, dt, and f of t, dt. So units of f of t, what does f of t represent? F of t represents the rate at which your 401k changes in value over the month of February. So what kind of units are we going to have there? Your 401k changing is dollars over the month of January. So since it's over the month, we're actually going to talk it day by day. So dollars per day. dt, remember that's kind of like delta t. That is your change in time, which is going to be in terms of, our time here is month of January, or in other words, we're talking about days. Now, f of t dt, that is f of t times dt. What is f of t times dt going to result in?
Squared.
Okay, if it's dollars per day times days, days will cancel and we'll just be left with dollars, money. Okay. The integral from 1 to 31 of f of t dt represents the total change in what? Let's put it in words. And some of it's kind of already there, but the total change in, what are we changing? Dollars, which we're talking the value of your 401k here, which is your dollars, okay? So the value of your 401k in dollars for how long? What does this 1 to 31 represent? The 31 days in January. So for the month of January. So it represents the total change in the value of your 401k in dollars for the month of January. Total change in, should have written this down ahead of time, the value of your 401k in dollars for the month of January. B when you're ready. If R of T represents the rate at which your pizza changes temperature in a 475 degree pizza oven 5 minutes after the pizza had been placed into the oven to cook. So the integral from 5 to 20 of R of T with respect to T represents the total change in, what are we representing here? What's changing? Temperature of your pizza, right? And what kind of units? Degrees Fahrenheit, right? Okay. So temperature of your pizza in degrees Fahrenheit. What's that 5 to 20 mean?
From 5 minutes to 20 minutes.
Okay, from 5 minutes to 20 minutes. It's 5 minutes after the pizza has been placed in the oven, right? So from 5 minutes to 20 minutes. So represents a change in the temperature of your pizza. And I am going to say in degrees Fahrenheit from T equals 5 minutes to T equals 20 minutes. And I'm writing that quick, and so it's getting kind of sloppy, but. Okay. Start reading C when you're ready. We have, what, I think 4 different questions based on C. Okay. You and your friends are planning to buy a ticket to your favorite music group, the New Tons. She likes her jokes. Everyone wants to hear their latest hit. Why integrate? If A of T represents the rate at which students are arriving at the ticket window, and P of T represents the rate at which they buy their tickets and enter the concert, then. Okay, what does the integral from 1 to 5 of A of T dt represents? A of T. So if you go up to the description, A of T represents the rate at which students are arriving at the ticket window, right? So, or
The time it takes for them to get their tickets.
well, not even in this case. A of T is just they're arriving at the ticket window. So this is just them getting in
So is
line.
so would ATDT, would that just be the number of students arriving at the ticket window?
Yeah, essentially
It's-
from 1 to 5. So from the time interval from 1 minute to 5 minutes. So it's the number of students getting in line, basically. How did I put it here? Number of students arriving to get in line from 1 to 5 minutes. Okay? It doesn't talk about them actually getting their tickets or how long they're in their tickets, but just the number of students that are arriving to get in line from 1 to 5 minutes. I just put number of students arriving in line. It's should be to get in line from 1 to 5 minutes. So I put 1 less than or equal to t less than or equal to 5.
What's the difference between this and then what we did last semester? Like, earlier.
And-
We would explain what the slope was telling us.
Yeah. Well, we were talking about derivatives there. Here we're talking about antiderivatives, which very similar. Here it's more, that was more rate of change. This is going to be more total change. So this is going to represent the total number of students arriving to get in line from 1 to 5 minutes, not the rate of the student. Does that?
Yeah.
I know there's a very fine line there. I get it.
So like one way to think about it, like they're giving us a derivative and then we take the antiderivative and that gives us what it is.
You can think of it that way too, yeah. What about if we change it to P of t? So now change functions. So P of t represents the rate at which they buy their tickets and enter the concert. The integral is that span from 1 to 5. Right? So this is going to be like what? How are you saying that? Like number of tickets
The number of tickets like of course.
bought and used then? Yeah, and I'm more going to talk about it's the number of students that buy the tickets and actually enter the concert. So, I mean, yeah, which does interpret to number of tickets, same idea. But yeah, so it's totaling up the number of students that have bought tickets and entered the concert between 1 and 5 minutes. So, number of students that have bought tickets and enter the concert from 1 to 5 minutes. So those were both integrals. It's a total change. So that one was a change from 1 to 5 of how many students have bought the tickets and entered the concert. A of t was the number of students that have arrived and gotten in line from 1 to 5. Now, excuse me. A of t minus P of t. Well, A of t is what? The rate at which the students are arriving at the ticket window. P of t is the rate at which they buy their tickets to enter the concert. So don't think, we're not looking at total change here. We're not looking at the integral. We're just looking at A of t and P of t. What's that going to, I don't want to ask this.
The backup.
Yeah.
The backup. So what's your line doing here? Getting longer or shorter, right? So this is basically your line growing and shrinking. Okay? It can be growing. It's going to be growing when the students are getting in line quicker than they're going through the line, right? It's going to be shrinking if you don't have as many students getting in line and you have more students getting through the line. Does that make sense? Okay, so this is your growing and shrinking. How did I put that? The rate the line is growing or shrinking. And we do need to say growing or shrinking because we don't know which one is bigger. Now, so that was an integral, or that was not integral. 4 is the integral. The integral from 1 to 5 of a of t minus p of t dt. And that's the total change in what? What?
The amount of students.
Okay, amount of students in line, which I have it written as the length of the line, right? Because your amount of students is the length of the line. So it's the total change in how many students you have in line, the length of the line. And of course, that is on the interval from 1 to 5 minutes. So I'm going to say length of line of students on the interval 1 to 5. Okay. And D. Start picking and choosing what we're doing. We've got a lot of notes left. Okay. Let's talk a little physics for a moment. Recall that velocity represents your velocity where the positive direction is to the right. Okay. Velocity is a rate at which what is changing? Velocity is the rate at which what is changing?
Position.
Position. The integral of v of t dt from 5 to 50 represents the total change in, this is position, on what interval? Mm-hmm. Okay, so change in the integral of velocity, change in velocity is going to be a total change in position on the interval 5 to 50, which has a special name in math called, I'm trying to think, would you have heard this in physics? I bet you have. Displacement? Is that our opinion of displacement?
Yes.
Or at least Megan's opinion?
Yes.
That sounds like she's representing, though. Okay. So displacement is the common vocabulary term to hear. I will say, I could also say net change. That could be an option as well. And last one, likewise, A of t is the rate at which what is changing? Velocity. I'm trying to figure out what I need to hit and skip and all that. I don't even know. Okay. And so, fundamental theorem of calculus. Fundamental theorem of calculus, what we were doing yesterday with evaluating when we have an upper and a lower bound, right? So, what we have seen, f of t has always been the derivative of f of x. In the next examples, we're going to explore some special cases where we may not have that specific relationship, and a general rule kind of for evaluating these expressions. Basically, when we look, and this is what we went back to doing the other day, we looked at some where the upper limit was a function, wasn't it? Okay, and when that was a function and the bottom was a constant, our shortcut was essentially just to take that that function and plug it in. And here's the key. Why can't we say that result is always that? Notice it's why can't we say it? Why can't you always just plug that in? And it will work sometimes, not always. The big deal is there a chain rule to think about? If there's a chain rule, it won't necessarily work. And that's where it gets a little nitpicky. Okay. We'll just go through these and see where we end up. With this example, find the derivative in two ways. And basically we're trying to figure out, do our ways equal each other? Okay, so with the idea f of x equals, what is that? The integral from pi to x of cosine t dt. So let's evaluate that integral. Okay. If we evaluate that integral, what is the integral of cosine? Or the antiderivative of cosine? The big key is a positive or negative sign, right? And it's positive sign. So it's going to be the integral of sine evaluated from x to pi. If we actually plug these in, right? If we evaluate using our fundamental theorem of calculus, then it's going to be the sine of x minus sine of pi. Evaluate upper minus lower. What do you know about the sine of pi? It's 0. Okay. And so f of x just ends up being sine x here. Okay. Now, over here in this column, we just found f of x to be sine x, correct? What would be the derivative of f prime of x? Or what would be the derivative? Derivative of sine x is cosine x, correct? Just derivative here.
Oh, I forget how to do that.
The problem when we start introducing antiderivatives. The derivatives all go out the window and we all get confused, right? So, yeah, that's the rough part. So derivative of sine is cosine. That's the one just going down. Now, with that being the case, do these end up equal to each other in terms of the fact that if capital F is the integral of, remember this would have been f of t dt right here. Didn't we end up with the same function? In other words, cosine, yes? So in this case, everything worked out fine. And it worked out fine when our lower bound was a number, our upper bound was some function of x. And so, what do I want to say here? How did I write it here? So, in this case, f of x, little f of x, does equal derivative big F. And so, what we can use from here is, this is our fundamental theorem of calculus here, that the derivative of the integral from pi to x of f of t dt is indeed going to equal f of x. And actually, instead of that bottom being x, I probably should have just put c for a constant. What do they use? They use a, don't they? So I really probably should just put a for some constant down there. But, so this is the idea. And when you take the derivative of an integral, the bottom piece is a constant, the top piece is some function of x, or it does end up being just whatever this is with that function plugged in. Okay? Now, with that in mind, what you need to notice here is my top was x that we plugged in. X is just a plain old x. If I had to do the derivative of x and think chain rule, the derivative of x would just be a 1 and not affect anything, right? Okay, keep that in mind as we look at the next one. And as we look at this next one, we're going to do a similar piece to the other one in that we're going to work through and find it. Now, okay, integral of the square root of 1 plus t. Well, that is 1 plus t to the 1/2 currently, yes? So what's the integral of 1 plus t to the 1/2? 1 plus t to the, add 1 to the power, 3/2. Then what do you have to do also? If you add 1 to the power, you get 3/2. We're dividing by 3/2, which is 2/3. So 2/3, 1 plus t to the 3/2. And that's evaluated from 0 to x cubed. Okay. If we plug this in and evaluate it, so plugging in x cubed first and then 0 next, 2/3 times 1 plus x cubed to the 3/2 minus, and then plug in your 0, 2/3 times 1 plus 0 to the 3/2. That's our evaluation piece there, right? Now, that first part, the 2/3, 1 plus x cubed to the 3/2, that's just that. That doesn't, we're not really going to clean that up for the purposes of what we're doing right here. What about this other part? 1 plus 0 is 1. 1 to any power is still going to be 1 times 2/3 is just going to make this minus 2/3, right? Okay, so that is our capital F of x. Now, if I take capital F of x over here and I reverse it and find the derivative, let's look if it matches. So I just copied what I just had. Okay, now we have to take the derivative. Can you switch your brain around? What's derivative say? Multiply the power out front. What's 3/2 times 2/3? 1. Derivatives, are you with me? 3/2 times 2/3 is just going to be 1. Keeping the inside, 1 plus x cubed. Subtract 1 from the power. 3/2 minus 1 is 1/2. And then what's the catch here before I move on?
The inside of it?
Then times the derivative of the inside. What's the derivative of 1 plus x cubed?
3x.
Because derivative of 1 is 0. Derivative of x cubed is 3x squared. And then officially there's minus the derivative of 2/3. What's the derivative of 2/3? And that is 0, nothing. Now, I mean, if you rearrange this, okay, you can put the 3x squared out front, and it's the square root of 1 plus x cubed. Does that match what our original was? Not exactly, does it? In terms of, like if I put in, if I do the x cubed in here, yeah, we've got this is your f of t right there, right? You've got the square root of 1 plus x cubed, but what's the difference? Bless you. We don't have that 3x squared, do we? And so that's as a result of the chain rule. And so this is one that, because of that 3x squared, like 1 plus x cubed, this will be 1 plus x cubed, you plug it in, that's fine. It's this piece right here. And so because of that, my f prime of x does not equal, capital F prime of x, sorry, does not equal lowercase f of x. So this is one where we can't just use the rule of plug it in, okay? There'd have to be that chain rule piece. And that's what you'll see, I think it's on the next page when we kind of summarize into some rules, okay?
What are we trying to do here?
I'm just trying to show you some examples to realize the differences. Like the last one versus this one. They both have constants on the bottom. The difference was that last one just had x as the top boundary. Chain rule of x isn't going to change anything. This one here has the top boundary as x cubed. Chain rule of x cubed will change something, won't it? And so our results ended up not the same. Okay? Now, the difference when on this one, let's see, would it be best to show it here or? I don't think it matters. We have two boundaries. Did we talk, I'm trying to remember, my days are blurring together. Did we talk yesterday about splitting that up or no? No, I don't think we have yet, have we? Okay. So here, in this case, both my upper and lower bounds are functions. Okay, they're x's. Because of that, we need to think about splitting this up so that we can use our fundamental theorem of calculus. Fundamental theorem of calculus only is going to apply, though, when the bottom one is, this is part one, when the bottom one is a constant and the top one is a function. So using the rule where we can, remember, if they have an overlapping boundary, you can add two integrals together, yes? So I can split it apart in the same way. And so I'm going to make a, what do I want to say, arbitrary variable here. Just going to pick a. And so I'm going to say the first one is x squared to a of sine t dt plus, and then I'm going to do the integral from a to cosine x of sine t dt. Now, after you see that split up, does that make sense? This is that rule where we could take these two and add these because the a's, the upper a and the lower a overlap, right? So you can take these and add these and make it one. I'm trying to split them apart. To use fundamental theorem of calculus part one, we need the function on top, the constant on bottom. A is just a constant. How do we make that happen? How do we flip-flop those? That's the negative, right? So I'm going to rewrite this now as the negative of a to x squared of sine t dt, plus the other one stays the same, the integral of a to cosine x of sine t dt. If we evaluate these, what is the integral of sine?
But
I say, you've got 50-50. Is it negative or positive cosine here, right? So traditionally, we know it's cosine, right? If we say the derivative of cosine is negative sine, and that's ignoring this negative out front, I assume? But we do have a negative out front, don't we? So can we make the negatives cancel each other out, make it a positive cosine? So this first one is going to be cosine of t evaluated from a to x squared. Okay. Yes, we should be saying negative, but there's already a negative out here, so I made it positive. And then plus the integral of sine down here. This one's going to be negative, right? Because there's already just a plus sign, so it's going to be the negative cosine of t evaluated from a to cosine x. Okay, if we evaluate these and plug everything in. Cosine of t evaluated from a to x squared. Excuse me, cosine of x squared minus cosine of a. Then this next one, it's plus negative, so I'm going to say minus. I'm going to start parentheses, and it's going to be minus the cosine of cosine x minus cosine a. I know there's a lot of pieces there to keep track of. Clean it up. Do the cosine a's cancel or add? They cancel, don't they? If you have negative cosine a minus a negative cosine a, so they're going to cancel. So I end up just with cosine of x squared minus cosine of cosine x.
You think the double cosine?
The input to cosine is cosine. You're putting cosine into cosine. We saw it on occasion in pre-calc. Not very often, but we saw it on occasion. Now, what we've been doing to see if this works. Take what we just got. So, f of x, capital F of x being cosine of x squared minus cosine of cosine x, and take our derivative. Lots of chain rule action happening here. Derivative of cosine of x squared. Derivative of cosine of something is negative sine of x squared times the derivative of x squared, which is 2x. Minus, what's the derivative of cosine of something?
Plus sine.
Okay. Normally the derivative of cosine is negative sine, isn't it? So minus a negative, this is going to be plus the sine of cosine x. That inside stays the same. Times the derivative of cosine x, which is negative sine x. It's a little messy, isn't it? Now, my cleanup. Negative sine x squared times 2x. I'm going to rewrite it as negative 2x sine x squared. Here I'm multiplying by a negative, so I'm going to say negative. And I think I probably, I don't know, sine x times sine of cosine x is probably how I have it written in my notes. Did this get me back to my original? Not at all, did it? There's a lot of messy chain rule action there, and I mean, yeah, I could factor a sine out, but then I've got all that other stuff there, don't I? So there's another situation where capital F prime of x does not equal lowercase f of x. And again, that goes back to using, that's your f of t, plugging x in there. Okay? Now, with that said, what it comes down to is we have to think about chain rule here. And so if I look to the next page, okay, make sure I can flip here. Okay, so can you see the need for the chain rule in some cases? First case, we didn't need it. The other cases, we did. You have to watch for that. So the idea here that when you are plugging a function into a function, you have to think of the chain rule. And actually, I was going to write up there. So right here, general form, what you're going to see, this is a function plugged into a function, but times the derivative of whatever you're plugging in. And so there again, that is your chain rule at work. Notice this is your example when your lower bound is a constant. Okay, so that is your example of lower bound being a constant, or lower function is a constant. This one, both pieces are functions. Neither of them are constants. Okay, this is your example here, where they talk about g of x and h of x. So in this case, where they're both functions, you'll notice it's the upper plugged in minus the lower plugged in. I forget if we use those in the notes or in homework, or probably a little bit of both. Okay, example 4 here. So this will use one of ours, trying to find the derivative of capital F of x based on it being in this setup here. Well, lower boundary is a constant, yes? Upper boundary is a function, so we're using the top setup here. Okay? Again, when we learned that fundamental theorem of calculus the other day, basically the 0 is going to end up canceling out and not mattering, right? When the bottom's a constant, the upper's a function. So you're taking e of t squared, but what are we plugging in for t? X squared. So it's e to the x squared squared, if you will, because we're plugging x squared in for t. But then that's plugging g of x into f, but then we have to do times the derivative of g of x. So what's the derivative of x squared? 2x. Okay, that's your shortcuts there. Now, if I clean this up, 2x e to the, what's x squared squared? X to the 4th. A power raised to a power, officially you multiplied there. I guess if you added, you got the same answer, but officially you should have multiplied. So that's an example of being able to use that, the fundamental theorem of calculus, and not having to go through all the work there. Okay. What is important in the next 5 minutes when I have a page and a half left to go? There are a few that say use a calculator in homework. So beware of that. Let's see. A couple of things I'm going to point out real quick. This one right here. This says evaluate the integral, if possible, that's a hint, from -3 to 6. What do you know about 2 over x? X in the denominator means x cannot equal 0. So does this integral exist across that whole interval? It does most of it, but not at x equals 0, right? So this is going to fall into a situation where the graph is not continuous. So this is not defined at x equals 0. We cannot integrate here. Does that make sense? Since x cannot equal 0, I'm just writing this basic because I'm running out of time. Not continuous. And I'm going to say, thus, cannot integrate on that. I need to say cannot integrate on the interval -3 to 6. Am I saying you can't integrate at all? You can integrate, just not when x equals 0, and that's on that interval there. Okay? There's one other piece I wanted to jump to and talk about real quick. Oh my gosh. On this one, we have a piecewise function here, right? So piecewise function being this piece over here is 3x squared, right? Y equals 3x squared. This piece over here is y equals 5. Given that you have the two pieces, what are we going to say about the integrals? Well, from 3 to 8, which this one goes on here, 3 to 8, you would be okay. You can integrate, and from 3 to 8, you would be integrating the what? Which one's bigger than 1? 5 dx. What about negative 2 to 4? We have the gap there, right? But because we have the two pieces, you can set this integral up to go from negative 2 to 1, and then the integral from 1 to 4. From negative 2 to 1, we're using which piece? You're using the piece less when it's less than 1, so 3x squared dx. From 1 to 4, using this piece over here, so 5 dx. Okay? Remember, the notes answer key is up if you want a little more information on that I'm not covering right now. Now, did I leave any time or not? 8. F is an antiderivative. Let me set up at least the basic for you, such that f of 1 is given, find f of 0. You need to think about the integral. What x values did they give me? From 0 to 1 of cosine of x squared over e to the x. Now, you're not evaluating that. Don't think, oh my gosh, I have no idea how to do that integral, Mrs. Sargent. Good, I don't want you to know how to do it. This is integration with a calculator, yes? Now, if you would integrate this, what is the idea? You take this integral, and then what do? You plug in 1, and you plug in 0, and you subtract them, yes? So f of 1 minus f of 0. Okay, this you can find on your calculator, right? Your calculator will do all that lovely math for you. What's it say f of 1 is? That equals 1/3. Minus, what did they ask us to find? F of 0. You know what my calculator tells me this lovely fun thing is? 0.59005. That's way too much. Could you find f of 0 at this point? I know I'm going fast, but do you see where I'm just basic algebra?
Yeah.
In order to find f of 0, I'm going to do what? 1/3 minus that 0.59 number. You're going to see a couple of those in homework, which is why I wanted to talk about it real quick. Okay? So does that, I don't know, does that help or did I just confuse? Maybe a little bit.
Do we have to do all this like stuff we just did each problem? Like this box, these boxes?
No, not necessarily. You're more applying the rules. So 1 through 8, or what we, actually 1 through even 16, a lot of that is just integrating. Being aware of some of the rules, but no, 1 through 16 is all just integrating. Some of what we just did pops up in 17 through 20. Some of that pops up here. 21 through 26 is more like what we are looking at, but use the rules there. So when I say use the rules, I'm talking about, where can I get to the page? Those rules. When you have functions as boundary, use those rules. If there's just a function up here, try and do this. If there's function both places, try and do that. That's what that back page is there, if I recall. Okay? Try it. Come back with questions. Obviously, there will be some. We'll see what happens. May have to do some reteaching on that one.
That was some slide.